Hi, welcome to 7.09. We're going to take our understanding of integration and apply those concepts to analyze some real-world situations. Okay, so to help put these ideas together, go ahead and work through this problem on your own. Copy down the important information and answer parts A, B, and C. Alright, so the first thing we're going to take a look at is this integral, this definite integral here. And remember, at the very beginning of the unit, we took a look at some velocity curves, and we came to understand that the area underneath them represents the change in position. So this here is going to represent the amount the position has changed from the starting point t equals 0 to t equals 10. And now with this in mind, we can actually represent this as an expression. Remember that the fundamental theorem of calculus tells us that to evaluate a definite integral, we need to evaluate the antiderivative of velocity at 10 and at 0 and take the difference. Well, what's the antiderivative of velocity? It's position. So this just boils down to the position at time 10 minus the position at time 0. Which of course is going to give me the amount the position has changed. The difference in position at 10 from 0 is going to be the amount the position has changed in those first 10 seconds. All right, now I want to write an integral that represents the amount the particle's position has changed from the start to any time t. So what I'm going to do is, thinking about this construction here, I now want to represent my upper limit as a variable, t, so that at any time t I can evaluate this integral, and that'll tell me the amount the position has changed between 0 and that time t. So it'll look something like this. Now notice that I had to change the dummy variable inside my integral so that my variable for this expression could be t. So this way, when I choose my value of t, that determines the upper limit of my integration, and I'll then take the area underneath my velocity curve between 0 and that value. And notice that we can evaluate this definite integral using the fundamental theorem of calculus so long as we can find the antiderivative of velocity, in other words, position function. So we'll take advantage of that as we start writing integrals like this. Alright, last but not least, we want to put this sort of all together. What do we need to incorporate with our answer from part B so that we can write the function s of t, which gives the position of the particle at any time t? So notice that this doesn't give the position at any time t. This gives the change in position. How much has the position changed from 0 to t? But we have to incorporate where the particle started, right? We could have started at x equals 100, and then if this change from 0 to t is 5, we'll be at the point 105. So in other words, we need to take the change, and we need to add that on to our initial position. So we can write this very easily. The position in terms of t is going to be the initial position, 5, plus however much I've changed in position from 0 to that point t. And so all of a sudden I have a very nice way, given a velocity function, to write a function that gives me the position. And because I know how to evaluate a definite integral, so long as I can find the antiderivative, this piece here can actually be done quite simply. So we can extend this idea now to really any situation where we're dealing with a rate of change. Let's go ahead and talk about how we'll view that. Alright, so we can use the fundamental theorem of calculus now to really concretely understand how the definite integral helps us evaluate real-world situations. The definite integral of the rate of change of a quantity over an interval is the change of that quantity over that interval. So concretely, if I have some function f, which represents the amount of a quantity at any time, then the definite integral from a to b of its rate of change, f prime of x dx, is simply equal to the change in that quantity from a to b. In other words, lowercase f at a minus lowercase f at b. And this is for any quantity that I have. So to be very clear here, the rate of change of the quantity is represented here by f prime. The interval, of course, is from a to b. And the change of the quantity, so the quantity is being measured by f of x, right? That tells me how much I have at any given time. And so the change is going to be the difference between f of a and f of b. Now, if you understand this relationship deeply, you can answer pretty much any question on the AP test that deals with this concept. And from this concept will sort of come all of the nice things that we do using a definite integral to evaluate any real-world situation. So it's worthwhile to take this and really digest it. In fact, this is what the AP test creators put out there as what needs to be understood about a definite integral in order to solve the problems on the AP test. So let's take this now and let's extend it a little bit so that we can kind of more easily build things that will help us out. So using this concept now, we can apply integration to write a function for the amount that a quantity has changed from a point A up to some point t. So let's start by representing that in terms of our function f. So f measures the amount of the quantity at any time. So the amount it's changed between a and t is going to be f evaluated at t minus f evaluated at that point a. And using the fundamental theorem of calculus now, we can represent this as an integral, right? This is just the integral from a to t of the rate of change f prime of x dx. Okay. Now, since this gives us the amount the quantity has changed, all we need to do is incorporate the amount we have at that instant A, and if we add that to the change, then we're going to have a function that gives us the exact amount of that quantity at any time t. So you can see this actually right here. This is a function, f of t, right, that gives us the amount of the quantity at any time t. If we simply add f of a to both sides, we will have solved for the function f of t. In fact, that'll give us the exact amount, right? So let's go ahead and write this out. What we will have is a function, f of t, which is comprised of the amount of the quantity at a plus the change in the quantity from that point A to any point t, which is the definite integral from a to t of the rate of change f prime of x dx. And hopefully now you can clearly see how this equation comes straight from the previous one, which of course came from our initial understanding of how to apply the fundamental theorem of calculus here. However, I like to think of this in terms of building my function given the amount at point A plus the change between that point A and any point t. I think that just makes more intuitive sense when you're building a function. And now we can apply this to any situation. We, in the discovery problem, applied this to velocity, right? And this is probably the classic example, right? Velocity is so clearly defined as the rate at which the position is changing. And so we can build the position function if we know the position at some point A and we know the function for velocity, so that we can find the change in position from any point A to some point t. And we can combine those two to create the position of my particle or my car or whatever it is at any point t. Okay, so now let's go ahead and start applying this. Before we do, there's just one term that I think is worth quickly defining because it shows up quite a bit. All right, so this term here is called displacement. You've heard it before. And displacement is defined as such. A change in position is a displacement. So if s of t is a body's position at time t, and we use body here just to represent, it could be anything. So s of t is just the position function for some object. The displacement over the time interval from t sub 1 to t sub 2 is simply the position at t sub 2 minus the position at t sub 1. Now there are a couple things to notice here. Displacement can be either positive or negative, right? Imagine you have a particle traveling on the x-axis, and at t sub 1, say your position is at x equals 2, so it's to the right of the origin. But then it travels to the left, and so its position at t sub 2 is maybe at negative 6, right? So negative 6 minus 2, that's going to be negative 8, and that means your displacement is negative 8, which you can interpret as you've moved 8 units to the left, between those 2 points. So it's important to remember that this can be either positive or negative, and you will interpret this, right, as a direction, right? What was the direction of that change? Now, the next thing that we notice, of course, is how this displacement is just the position function s at t sub 2 minus s at t sub 1. In other words, this can be written as a definite integral, right? Where I'm taking the definite integral from t sub 1 to t sub 2 of s prime. So let's go ahead and write this out. We have the integral from t sub 1 to t sub 2 of s prime of t dt. And of course we know that s prime of t is just velocity. So we can interpret this more concisely as the integral from t sub 1 to t sub 2 of the velocity of that particular body, dt. Okay? And this, of course, is just going to be equal to the position at time 2, t sub 2, minus the position at time t sub 1. Okay? But the nice thing is that we can think about displacement as a definite integral. So when we're trying to find displacement and we have, the velocity of a particular body, we can still find the total displacement between 2 times using the definite integral and then evaluating using our fundamental theorem of calculus. Okay, so now you know what is meant by displacement. Let's go ahead and take a look at a couple of examples so we can apply what we've learned. Okay, so a particle travels along the s-axis, so that its velocity is given by the function b of t below. Suppose that the particle is at s equals 4 and t equals 0. All right, go ahead and find the displacement of the particle from t equals 0 to t equals 4. Find the function s of t, and then find the position of the particle at t equals 5. Go ahead and work on this on your own first, and then we'll take a look together. All right, so displacement is the definite integral between those 2 times of the velocity. So we're going to need an antiderivative for the cosine of pi t, and I know that the derivative of sine is cosine, so I'm going to start with sine of pi t. But notice, if I took the derivative of this, I would get cosine of pi t times pi. And I don't have a pi here, so I need to multiply by a 1 over pi, or in other words, I can just write it as sine of pi t over pi. And I'm going to evaluate this at 4 and at 0 and subtract the 2. And this is easy enough to write, so we'll go ahead and write it down now. And we can evaluate this quite easily. 4 pi is twice around the unit circle, so we're back to the beginning of the unit circle, and sine at that point is 0. So I have 0 over pi minus 0 over pi. 0 minus 0 is 0. Okay, take a second now. The displacement of the particle between these 2 times is 0. What does this mean about my particle? This is actually pretty simple. This means that the change in position of my particle from time 0 to time 4 is 0. In other words, it's in the same place it was at time 0, again at time 4. So I want you to actually go ahead and write that down in your own words now, so that when you go back to this example and you interpret this displacement of 0, you can do so. Okay, so now we want to write the function s of t. Okay? So s of t represents the position. So consider how I could build the function that represents the position, s of t. Well, there's going to be 2 components here. The first is that since I know the velocity, right, I can compute the displacement between 0 and any time t. Okay? But I'm going to need to also incorporate the fact that at time 0, the position is 4. So I'm going to add the displacement between 0 and any time t, the displacement 0 and 4, I'm going to add that displacement to the initial position. So I will have s of t, which is equal to s of 0, I'm going to represent it this way first, plus the displacement, so the integral from 0 to t of v, and here I have to use a different variable, v of x dx. Okay? So what is that? Well, the initial position here, s of 0, is 4, so I'll have 4 plus the integral from 0 to t of cosine pi x dx. All right, but think about this. Can we take this a step further? So this works perfectly fine, but every time I plug in a value for t, I'm going to have to evaluate this definite integral. So can I evaluate this definite integral? Well, I can find the antiderivative, I just did that, and I can evaluate it at t and at 0. And that will actually give me a much easier to work with, at least without a calculator or a computer, expression. So let's go ahead and evaluate that now. So it's going to be 4 plus, and here I'm going to evaluate my integral here, so I'm going to use this closed bracket. So I'll have the antiderivative, which is sine of pi x over pi, evaluated at t and at 0, and then the difference between the two. And this will give me 4 plus sine of pi t over pi minus sine of pi times 0 over pi. Well, notice sine of pi times 0 is always 0 because it'll be sine of 0. So this will end up being a plus 0, and I'm done. This is my equation, my function for position. So I can rewrite my position function. S of t is going to be, and I'll write this piece first now, sine of pi t over pi plus 4. All right, now quickly I just want to note how this expression is the exact same as this expression here. It's just that we've evaluated the definite integral. So if I'm computing by hand, this is much easier to do than repeatedly doing this process here. However, this is just as valid a function. All right, what is the position of the particle at time t equals 5? Well, here we see how we can use this to compute part C. So go ahead and use that function to compute the position. And I end up with 4.318 approximately. So we can see that at after 5 seconds, it's a little bit further to the right than where it started. All right, let's take a look at one more example. All right, a car moving with an initial velocity of 5 miles per hour accelerates at a rate of 2.4 t miles per hour per second for 8 seconds. What is the velocity of the car after 8 seconds, and what is the displacement of the car over the first 8 seconds? So I want you to try this on your own, but before you do, make sure you have, before you jump into these questions, make sure that you have a clear understanding, sort of the picture of what's happening. The car is traveling at 5 miles per hour, and then it starts accelerating. And if you notice the function for acceleration, at any time t, we're going to have some positive acceleration. So your car's velocity should be increasing fairly quickly. All right, hopefully that went well. Let's think about velocity of the car after 8 seconds. So we know the velocity of the car at the start, 5 miles per hour. Now, how could we find how much the velocity has changed from 0 seconds to 8 seconds? Well, we know that we can interpret the definite integral of a rate of change over some time interval as the amount that that quantity has changed. And since acceleration is the derivative of velocity, meaning it measures the rate at which velocity is changing, we can find the change in velocity from 0 to between 0 and 8 by taking the definite integral of our acceleration function from 0 to 8. So let's go ahead and do that. All right, and this will give us the change in velocity from 0 to 8 seconds, but we also want the total velocity of the car after 8 seconds. Remember, it started at 5 miles per hour, so we'll have to add 5 to this. And now we can go ahead and evaluate to find the exact value here. So go ahead and do that now on your own. All right, when you evaluate, as you can see going through these steps here, pretty straightforward. I factored out the constant to make the antiderivative work a little easier. When I evaluate this at 0, I get 0, so that takes care of it. I only end up with 64 over 2, which is 32. And then when I add on 5, I end up with a total of 81.8. And so this is the velocity, which is miles per hour here. So after 5 seconds, the car will be traveling at a velocity of 81.8 miles per hour. Now, part B, we want to find the displacement here. Okay, so remember, we know that displacement is the definite integral, in this case from 0 to 8, of the velocity. Okay? Well, we don't have a function for velocity, we just have a function for acceleration at this point. But we've actually come pretty close to doing that right here. Notice that what we did is we took the change in velocity between 0 and the point 8, time 8, and added the initial velocity. So we can write a function for velocity quite simply using basically the same construction. We'll have the initial velocity plus integral from 0 to t, and here I'll need to just change, so this will be a, the acceleration of x dx. Okay, and we can go ahead and evaluate this rather simply here. So I'll have 5 plus, I already know the antiderivative of this acceleration function, right? Basically this step right here. And so what I have is 2.4 times, and the antiderivative here, which is going to be x squared over 2, because remember now I have 2.4x, not t here. So x squared over 2 evaluated at t and at 0 and subtracted, and then I can go ahead and compute that, simplified a little bit, so that I can write my velocity function. So it will look like this. Notice, of course, that I had 2.4 over 2, which ended up being 1.2 t squared plus 5. And now, to find the displacement, I can just take the integral, definite integral of this function from 0 to 8. So once I set up my definite integral and evaluate, I end up with 244.8. We got to be careful here, because you might say, okay, the displacement was 244.8 miles. Well, that would mean that your position has changed by that many miles in 8 seconds. And I kind of don't think that your car is quite that fast, particularly based on its acceleration here. So we need to take stock of the units here. Remember, velocity is measured in miles per hour. So if you imagined a graph here, and really what we're doing, we're kind of multiplying the velocity by the distance of seconds that have elapsed. So we have miles per hour times seconds. So it's miles per hour times seconds here. And usually we end up with, we're using the same number of, or the same units to count our interval as we are to measure our velocity. But we're not here. So, if we used hours, this would make sense because we'd have miles over hours times hours, and that would just leave us with miles. But here we don't, so we need to consider what we'd need to do in order to straighten out our units here. So let's take a look here. We have miles per hour times seconds. Okay? And we want this to end up with just miles. So what do we need to do here? We need to multiply by hours over seconds. So we need to multiply by hours over seconds. And you might start off by saying, okay, well, how many seconds or how many hours are there in a second? That doesn't make it so useful, it's easier to think if you had 1 hour, how many seconds would there be? Well, you have 1 hour, there's 60 minutes, and each minute 60 seconds. So 60 times 60, 3,600 seconds. So you'll need to multiply your 244.8 miles per hour seconds times 1 over 3,600 hours per second. And that way, hours over hours, seconds over seconds, you'll end up with a certain number of miles. So if you do that multiplication, you're going to end up with 0.068 miles approximately. And you might say, okay, well, does that make sense? Well, it's certainly feasible, it seems like. And you could convert this to feet, and you'd get approximately 359 feet, which I think makes a little more sense since you've only been traveling for 8 seconds. The displacement, or the change in position from 0 seconds to 8 seconds, will be approximately 359 feet. All right, at this point, go ahead and move on to homework 7.09.